it's Plumber Tom. Don't forget to check in the comments below for a link where you can find additional resources like practice tests and courses you can take. Your support helps me to be able to create more great content. Thanks for watching. Hello, welcome to this presentation of mathematics for plumbers and pipe fitters. My name is Thomas and we are on Unit 35, which is titled Jumper Offsets. Now, what is a jumper offset? Basically, if you have something round like a column or a tank or something of that nature, and you're trying to move the pipe around it, to offset around it, then there are some special math methods that you can use to get it perfect. This is math for the professional plumber. This is math for those who really want to show they have mastered this trade. I'm pulling straight into our sample problems here to show you what a jumper offset is all about. There are two ways that you can accomplish jumper offsets. One is with 90s and 45s. You see we have two 45s. They send that pipe out around this round tank object column, whatever it is, and it's connected by a 90. You can see the triangles that this creates, and there's enough geometry in here for us to be able to make our calculations and get around. So this is the first version of a jumper offset. The second version of a jumper offset is found in the third sample problem, and this is an offset using 45s to go around this round object. We had our pipe running along, the 45s send it out and around. There's two 45s that create a 90, but they're kind of spread out, so you can see it's more a trapezoidal shape as it moves around this. What we're doing here is eyeing up the opponent, right? You get out there, you watch those boxing matches, and they're going to look each other over first, trying to figure out, like, what's this guy all about? What's this going to take? How am I going to take this down, right? That's what we're at right now. A quick overview. This is what we're going to take on today. Okay. There is a lot of math in these, and they're challenging. It might feel like a giant to you, but put these in your pocket. These are the tools for your tool belt. These simple formulas are what we're going to use to dissect and take these down. Here we go. Diagonal. To get the diagonal, you times the offset by 1.414. You totally know this one, so hold on to it. Offset. You can go backwards and get the short side of a 45-degree triangle by multiplying the diagonal by 0.707. That's going to be useful to us today. We're going to be using a secondary square. We will superimpose a square onto this whole picture, and we can use parts of that square to get a diagonal. So our diagonal would equal 2 times the side of this square. We just cut this square in pieces and then go, okay, this side of the diagonal is going to be 2 of these sides of the square. I'll show you. That'll make sense here in just a minute. And finally, you're going to need to use 0.414, which is the constant for a 22-degree angle when we're using 45-degree fittings. Now, that also will make sense to you in just a few minutes. And this one you're going to hang on to for the next 2 units, 36 and 37. We're going to be relying heavily on that number, 0.414. Let's jump to the back of the book. We've got a data table that's going to show us what that constant is all about, what it's used for. We'll put that in your tool belt, ready to roll, and we'll start taking these on. Now, if you haven't spent much time in the back of the book, the appendix has a lot of useful tables and information. Good idea to get to know them. Wouldn't hurt to flip through that once in a while. I'm going to take you right to data table 20. This is on page 281. Go there with me. Make sure you have your book open. This has the constants for 45-degree fittings. This is a triangle we deal with all the time when we're in the lab, when we're doing regular offsets with 45-degree fittings. And it gives us those constants that we use, right? Diagonal equals 1.414 times the offset or the rise. And if you want to go backwards, you can take the diagonal, if you already have that, times it by 0.707. It will give you both the rise and the offset. So this is a useful one. But flip with me to the next one. This is data table 22, constants for 22.5 degree fittings. This is on page 283. You can see we have one vertical version of this triangle. A triangle that has a 22 degree fitting and a 90. And there are some constants, just like our 45 degree offsets and all of that. We're using 1.414. This is a different triangle, but it also has constants that we can use to find different sides. Let me point out on this triangle, we have several things going on. We have the offset, that's the short side. The rise, it's a little bit longer, and then the diagonal. Now, if I know what the rise is on this triangle, or let's look at the horizontal version. Here's a horizontal of the same triangle. We're going to call it the run. If I have the run on this triangle, and I need to know the offset, that's the short piece, I can take the run and times it by 0.414, and it will give me the offset. Is that making sense? Take the run, times it by 0.414, it will give you the offset. Same thing will happen here with the rise. If I take that rise and I times it by 0.414, it's going to give me the offset. That's the piece we're going to need as we're defeating these jumper offsets and all of the offsets we do in the next two units, 36 and 37. Let me point out, though, this is not hard to remember because you always use 1.414. And when we come to these 22 degree angles and we're trying to figure out offsets, just take off the 1. You've got this number already, 0.414. So hang on to that one. Let's get to the sample problems. Round 1, we're going to start off simple with sample problem number 1. Simple in that our pipe, as it's traveling along, lines up with the center line of this round column or cylinder, whatever we're going around. So what we're going to try to figure out here are what are the distances on J, center to center, and K, center to center. What do we have? What do we know? Examine the circle itself. The diameter of that circle is 8 inches. That's helpful information. We also want to space our pipe away from that circle 1.5 inches. Also helpful information. To figure this out, we need to know what A is. Do you see A? A is that diagonal distance from the center of the circle going out to the center line of pipe. You see that there at J. It's the same thing over at K. If I can figure out what that is, that's an excellent starting point for me to figure out J. Well, how would I figure that? If I know the diameter is 8 inches, then what's the radius? The radius of a circle is from the center line to the edge. It's 1/2. The diameter is the whole width. So I divide 8 by 2, and I'm going to get 4 inches from the center of the circle to the outside edge of the circle. And I can add to that the distance from the circle to the center line of pipe, which is 1.5. That's going to give me a total of 5.5 inches. Let's see what we can do with that. Note on the illustration on page 134 that we now have a secondary square. This is a square that we've been able to create geometrically from these different sides and angles that we're looking at. One of those sides we just figured out. You see it here, A equals 4. That's the radius plus the distance to center line. That was 1.5. We had 5.5. Now, what do you know about a square? A square has the same length sides all the way around, which means that if this side is 5.5, then so are all of the other sides. And if the other sides are 5.5, then we end up with a distance of 5.5 at the center point of these pipes that we're trying to calculate. I can take that side, center to center, which is 5.5, multiply that by 2, and it's going to give me 11. So what does that say? That tells me that from the center of the 45 to the center of the 90 on this jumper offset, I need 11. We see that in the sample problem. That's how they solve for J. Sample problem 1 gives us the opportunity to figure out one more length that will be useful to us as we're solving these other jumper offsets. And that is the side of these other triangles that are created. We figured the diagonal from fitting to fitting is 11 inches. But you see how there's another triangle created below? And it has a diagonal itself. One of the sides of those being the length of the side of the secondary square. What we're going to do though here is we're going to use our 0.707 on the diagonal that we figured, the 11 inches from fitting to fitting. If we multiply that 11 inches by 0.707, what we'll come out with is pretty close to 7 3/4. And that's going to be helpful. Being able to calculate this length here that you can see is going to be helpful in our upcoming sample problems and your exercises. You're going to need to know how to get that length as well. Now let's pause here and examine what we know about these shapes and how they come together. This is simple geometry. This is stuff we've studied from year 1. On this diagram, you can see a circle. You know how to get the area of a circle. You know the parts of a circle, a diameter, a radius. You also see a square on here. You know how to work a square. They're pretty simple. All the sides are the same at 90-degree angles. You also see triangles, and all the triangles we deal with here are right triangles with 45-degree angles. You know how to handle those using 1.414 to get the diagonal, or 0.707 to go from that diagonal back to one of the smaller sides. This is basic stuff, compounded over each other, but we use them to go back and forth. Do you see how awesome this is? We are thinking with shapes in ways that we have not been thinking before to solve a problem here. And it's pretty exciting when you know how to use these basic tools to figure out something a little more complex. Speaking of more complex, let's go on to sample problem 2 and try out something a little more difficult. All right, here we have sample problem 2. This time we're being asked to figure out a few more things. We have J, K, L, and M. Look at this diagram. Notice that there are a few differences, and this will create a little bit more complexity within this problem. One of the differences being that on the left side, the section J, the pipe is not actually on center line of the circle. It's kind of above that, in fact, by 1 inch, as you can see on the far left side. The pipe turned on a 45-degree angle towards the 90. This is section K. From the 90, it comes back down section L to a 45. And then we see the section M from the 45 to another 90. And section M here is below the center line of that circle by 1 inch. So we're going to be figuring things just a little bit different as we try and figure out J and M, as we figure out K and L. We're adding a few more steps to the sample problem 1. Let's get to it. Whoa, check it out. If you look real close at this diagram, there's a right triangle with 45 degrees. It's tiny, right there. Wait a second. Look, there's another one on the other side. I wonder if that would be useful to know later. All right, the first thing we're going to want to do on this sample problem is find the secondary square. That'll be our starting point for all of these sample problems. In this case, we have a diameter that is 10. So help me out here. what is the radius? Radius of that circle, you know it. You divide that by 2, and you're going to get 5, right? 10 divided by 2. Radius is half of that, so we have 5. Now, look closely. What is the spacing from the outside of the circle to the center line of pipe? I want to note that here our spacing is 2 inches. So that gives me enough of a basis here to find that 5 plus 2 equals 7. 7 inches is one of the sides of that secondary square. It's inside of all of these shapes, right? That's helpful to know. So then I'm going to say, well, I want to find that diagonal that goes from the 90 all the way down to the center line of that column. And we did that before on the last one. We just times that by 2. So we have 7 times 2. And that's going to give us 14 inches. 14 inches is the measurement from the 90, center of 90, all the way down to center line of pipe. That goes through the diagonal K and L. But we can't just hold on to that and say, well, like we found K. Because note, the K is actually shorter by just a little bit. And L is actually longer by that same amount. Each one of those is a 1-inch offset from center line. So, how do we find that? Take a look here. If we zoom in, we're going to end up with one of these triangles. Mine's not exact, but it's a 45-degree triangle, right? And the difference there, the spacing is 1 inch on one of those sides. This is easy stuff because we already know how to handle a 45-degree triangle. We take 1, times it by 1.414, right? And that's going to give us 1.414. What do we do with that? Well, if you look at K, it is short from touching the center line of where that circle is by the diagonal, by this distance from here to here. So when I figure that is 1.414, that's actually what I can subtract from what we just discovered. It was 14. 14 inches is what we get from the top of the 90 to the center line of that circle. And I can subtract 1.414. Let's convert this 1.414 into a fraction, as they do in the book. 1.414, we're going to keep the 1, but we need 0.414 into a fraction form. So if I multiply that by 16 over 16, that's going to put it into 1/16 of an inch. Bring in the calculator here, and we're going to have 0.414 times 16. That gives me 6.6. Let's round that up to 7/16. So what we're going to have there is 1 7/16 equals 1.414. I'm going to subtract that from 14. 14 was our measurement, again, from the 90 to the center line of that circle. We know that we're offset from that by 1 inch, and the difference is going to be that 1.414. So we're going to end up with 12 9/16. That is our measurement for K. We've solved one of them. Next, let's solve for L. And L is not going to be much different than K. I'm going to hold that whole same triangle we were looking at because L extends beyond the center line. By the same distance, 1 inch. When we take 1 inch, multiply that by 1.414, we get 1.414. We calculated recently that would be 1 7/16. And this time, to get L, we're going to extend that line. So if our measurement from the 90 to the center line of pipe was 14, as we're looking at L, and this time we're going to add 1 7/16, then we get a total of 15 7/16. That's it. That's L. Now let's see if we can figure out J. J is going to be that section from the 90 on the far left to the 45. Notice at the very bottom of the diagram, we have 15 inches. That's from the center of the circle to the center of the 90 on the far left side. Somehow we may be able to figure out J by this triangle inside of here. Notice that if we take K, which was 12 and 9/16, I'll substitute that in here, 12 and 9/16, and if we look at the fact that that is the diagonal for a triangle that would have a side that goes from the center of the 45 to the center line of that circle. Basically, we just need to go back to that 0.707. Real quick, let's convert 9/16 into a decimal so we can play with that. That would be 12.56 times 0.707. So if we take 12.56 times 0.707, we're going to end up with 8.87 inches. Let's convert that 8.87 into 16ths of an inch real quick. We're going to save the 8. We need 0.87 times 16 over 16. 0.87 times 16 is going to equal 13.9, basically 14 16ths. We can reduce that down to 7/8 as a fraction. Just divide both the numerator and the denominator by 2. We got 7/8. So we got 8 and 7/8. That's what we'll subtract from 15. 15 minus 8 and 7/8. Well, 15 minus 8 is 7. Minus 7/8 is going to leave us with 6 and 1/8. That is going to be our measurement for J. All right, next let's figure out M. If you look across the bottom of the diagram, there are 20 inches from the center of the circle out to the center of the 90 on the far right side of M. M is the distance between the 45 and the 90. I need to know the missing distance between the 45 and the center of the circle. The overall is 20. I can use what I know from L, right? We figured out L is 15 and 7/16. Let's convert that over into a decimal form. 7 divided by 16 equals 15.4. Let's round it up to 4. All right, what am I going to do with that? Well, L was the distance, a diagonal distance, from the 90 down to the 45. And if you remember, if I have a diagonal and I want to figure out one of the shorter sides on a 45-degree triangle, I can take the distance of the diagonal, which is 15.44, and multiply that by 0.707. And what does that give me? 15.44 times 0.707 equals 10.9, let's say 92 inches. Now, I'd like to get that into fraction form, so I've got 10 inches and that 0.92. Let's multiply that by 16 over 16, get me into 16ths of an inch. So if I go 0.92 times 16, that's going to give me 14.72. That's closer to 15. I'm going to call that 15/16ths of an inch. So that important measurement that I was dealing with was 10 and 15/16ths of an inch. That was that missing section from the center of the circle over to the center of the 45. So I'm going to subtract that. From the overall at the bottom, I have 20 inches. 20 minus 10 and 15/16. What's that going to leave me? Well, 20 minus 10 is 10. And then we subtract another 15/16. That's going to leave me with 9 and 1/16 of an inch for M. Woo, yeah. Woo. We made it through. We made it through sample problem 1 and sample problem 2. And it's taken us a little bit to get there. But hopefully you were able to follow me through each of these steps that we use to solve a jumper offset. Now the ones we've looked at so far use a 90 as it turns out and comes back. There are several exercises that correspond to sample problem number 1 and sample problem number 2. I'm going to invite you to stop here. And I'm going to stop this video before we go on to sample problem 3. Do the exercises that correspond to these first sample problems using a 90 to turn and come back. That'll give you some more experience before we go on to sample problem 3, and we'll look at how do you do a jumper offset using all 45s. 45s turning out, and 2 of them out there that are going to turn it back. So take some time, make sure you know how to do it with the 90. I'll see you in the next video where we'll go over sample problem 3, and we will go over how to do the jumper offsets with 45s. I'll see you there. What good is 7 1/4? Stop the video.